my pleasure to introduce Dafna Shahaf, today's speaker. Dafna got her PhD at Carnegie Mellon University working with Manuel Blum and our now recruited Carlos Gestrin. And she spent the last little bit in Palo Alto at Stanford working with Yuri Leskovic. And as you can all see on the screen above you, she's going to be talking about from data to insight.
Thanks. So I'm Dafna, and today I'm going to be talking about my recent project, the aha moment from data to insight. So what's the whole thing about? The thing is, there was a time not so long ago where getting your hands on good data was actually really, really difficult. Like this poor interviewer here that had to ride a horse across the country and ask farmers how many cows they had. And of course, today it's a completely different story, right? Today you have cows that tell you where they are and what they've been up to. So getting data is no longer much of a problem. We have more data than we know what to do with. And this is actually great news for everybody, right? Because large-scale data has this potential to transform almost every aspect of our life, from science to business and sports and public health, and it can really address some of society's most pressing problems. The thing is, for this potential to be realized, it's not enough to acquire this data. It's not enough to collect it or even to search through it. You actually have to understand it or to make sense of it. You really have to turn those heaps of data into insight, into actionable items. Okay, so this is where I come in. And my goal is to develop computational approaches for this problem of turning data into insight. And these are just some of the questions that I'm most curious about. Okay, for example, what is insight? And given lots of data, how do you help people understand the structure? Or what are the most interesting bits and pieces? And ultimately, how do you use this to build systems that will facilitate discoveries? Okay, let me give you an example of how the whole thing works. This is going to be in the context of news. Okay, so here's the scenario. Suppose you're trying to understand a really complex news story. Okay, the presidential campaign, the Greek debt crisis. So what do? Most of you would go to a search engine, right? We love search engines. Thing is, search engines are great at retrieving those nuggets of knowledge, but they're not going to show you how those 57 million results fit together. Right? There's absolutely no structure. Now, there's been lots of work about summarizing news and adding some structure, but most of this work boils down to a timeline, like this one, about the Greek debt crisis. And I'm going to claim that this style of summarization really only works with simple stories that are linear by nature, and that real stories are nothing like linear. Okay, if I had to come up with a picture of the Greek debt crisis, then it's not a single line. It's more like this. Okay, so what do you do with this spaghetti type of stories? Let me show you the Holy Grail. How many of you have seen issue maps before? Oh, more than I expected. Awesome. So this is an issue map. It's a set of 7 posters about a great AI debate about whether computers can think. Okay, let me just zoom in for a second. So it's really a graph where each node is an argument, like machines can't have emotions. And the edges tell you that this argument is supported by that argument, which is disputed by the other argument. So you're supposed to read through this and get a big picture. Okay, and I've stumbled across those at Carnegie Mellon. And I love this topic. I seriously love this. I just stood there for an hour and read throughout the whole thing. And it finally made sense. Okay, finally everything clicked in my brain. So I immediately started jumping up and down like, great, how do they make those beautiful creatures? And turns out it took 20 man years, and they did pretty much everything manually. So the next question was like, OK, so how do you build those automatically? Making sense? Good. So issue maps are complex creatures, so we started simpler. And the system I proposed is called metro maps. Okay, where the input is a set of documents. You can think about them the result of a query. Okay, here are documents about the Greek debt crisis. And the output is a map. Okay, with a map is a set of metro lines. So each line is a sequence of articles that follows a coherent narrative thread. Okay, so this one tells you how the Greek bonds are rated junk, and they had to come with the austerity plans to get a bailout. And different lines focus on different aspects. So you might have another line about how the austerity plans triggered all those protests and strikes, and another line about Germany. Okay, so you're really supposed to look at it and get the temporal dynamics and the structure. So what are the major storylines and how they intersect, how they interact. Okay, motivation clear? Good, so how do you go about finding those things? And in a way, finding maps is a really hard problem because you don't know what you're looking for. Okay, so if I show you a good map, then you know it's a good map, but it's a really intuitive property. So what I do, first of all, is trying to understand on an intuitive level, what makes a good map? Okay, what are properties of a good map? For example, each line is coherent. But then coherent is this really fuzzy notion. So how do you go about formalizing this mathematically? Okay, how do you come up with an objective function, something computers can play with? And once you have an objective function you're happy with, everything interesting I do seems to be NP-hard. So how do you go about optimizing it? Okay, how do you find some approximation guarantees? Okay, so this is kind of the flow, starting with intuitive level, formalizing, and optimizing. OK, so let's start with intuitive level. So what makes a good map? Just take a couple of seconds and think about it. Well, I guess I gave you the first property already for free, right? It's coherence. So each line follows a coherent narrative thread. But what does that mean? So luckily, we had an entire paper about the notion of coherence in KDD 2010, where the goal was, if you're given a chain of documents, how do you measure its coherence? OK? And I asked this question to a whole bunch of people, and they usually tell me that, OK, just a matter of strong transitions. Right? Make sure that the first one is similar to the second one, second is similar to the third to the fourth, and you're good to go. And the entire point of this paper is that strong transitions are not enough. OK? You have to go beyond local interactions. Let me show you what I mean. So bars here mean that the word on the left appear in the article above it. OK? So this is a document about the Greek debt crisis. Now suppose you want to build a coherent chain. So you're going to look for something that's similar to the first document, and you might come up with this one, what the Republicans think about the debt crisis. Now, if you completely forget about the first one and try to find a third one that's similar to number 2, you might come up with this one, what the Pope thinks about Republicans. And you're just going to drift farther and farther away. And you see this staircase behavior? This really means that the entire thing is kind of stream of consciousness. Okay, that every two things are related, but they're related because of a completely different reason. OK, let's try this again. Same article, Greek debt crisis. Same second article, what Republicans think about the debt crisis. But now you remember the context, and you know where you came from, and you know Republicans are not the main point. So you really stay much more on topic. OK, and you can see that the transitions are much smoother and nicer. You don't see the staircase behavior. And most importantly, there's a small number of words that capture the entire story. OK, let's try to formalize this. So in order for a chain to be coherent, we want two things. First thing is that each transition is strong. And this means that we need to define a score of a transition. So first thing we said was a transition between document di and di plus 1 is just the number of shared words. Okay, sum over words score 1 point if it's shared. This was way, way too coarse. Because, first of all, some words are more important than others. And also, words are kind of noisy features, right? Because you might have an article about judge and jury, but not lawyer. So is it really implicitly there? So we had to come up with a softer notion that we call the influence of word W on the transition between di and di plus 1. And intuitively, this influence notion is high if the two documents are related, and W plays an important role in what makes them related, even if it doesn't appear in either of them. Okay, just to give you a flavor, the way you formalize it, we made a bipartite graph between documents and words, and we looked at random walks between di and di plus 1, how important is the word W in those walks. OK, so this is the score for a single transition, and since you want all of them to be important, to be strong, you want the weakest link. Right? You want to make the weakest link as strong as possible. OK, so now we have that each transition is strong, but what about the second thing I told you? This global theme running throughout, a small number of words that capture the entire story. So we're really going to turn this into an optimization game. OK, just find this small number of words. So suppose I give you a budget of 3 segments, OK? And you're going to pick 3 segments, and I'm going to pretend that these are the only words that exist in the documents. OK, and so if you pick those 3, there's nothing between D1 and D2, right? So your weakest link is 0. But if you happen to pick those 3, then your weakest link is much stronger. Okay, in other words, instead of summing over all words W, you sum over words active. And activation is really the thing you're optimizing for. Okay, so we have constraints that try to imitate this behavior of coherent chains. Yeah, good. So this was our notion of coherence. And we solved this with linear programming and then some rounding. OK, we have the first property, coherence. At this point, you should be looking at this and say, well, OK, great. So are we done? Can I just pick the top 3 coherent chains and call it a map? So let me show you what happens when you actually try to do this. So this is the Greek debt crisis. And you see 1 line about Asian markets and 2 lines about the strikes and riots. OK, what's wrong with this map? Well, really 2 things, right? First of all, the Asian markets, we have a budget of 3 lines. And Asian markets are not the most important thing that happen, right? There are so many important things like Germany. And also, the bottom 2 lines are really redundant. There is no reason for the map to include both of them. So it seems like the challenge is to balance coherence with what I call coverage. OK, so the map should cover diverse things that are important to the user. OK, so what does coverage mean? So I keep calling it coverage. So let's talk about the set of items you're trying to cover. And you can think about them as words. OK, Obama, China. And you really have a probability score for each document. How well does this document cover this word? And this is based on TF-IDF scores. Last thing you have is a weight. How much do we care about this word? How important it is? And if you don't know anything, you can do it based on frequency. Everybody's talking about Obama. He might be important. But this is also a perfect place to plug in personalization. If I do know something about you, like you don't care about politics, but you love sports. And I said that that coverage should be about two things: about important topics that are diverse. And diverse really means a modularity, right? It has this diminishing return property. So let me just show you the idea. So this is the corpus here. So the size of a word corresponds to its frequency. And the idea is a document cover words. So you have this blue document here that covers some of Obama and some of Washington. And these are important words, so you get lots of corpus coverage. And you can pick another one that pretty much saturates Obama and US and New York. So now really you're not going to get much from picking another one about Obama. And the objective function should push you towards covering important words that haven't been touched yet. Okay? Okay, let's formalize this. So each document in the map tries to flip a coin, and with this probability manage to cover word W. Now, all of the map documents try to do this independently. This is the probability that at least one of them succeeded. Okay, so really this is the probability that all of the map documents covered a single word. Then you just sum over all the words, and you weight them by how much you care about covering this word. Okay, so really summing over the words, how much do we cover it, times how much we want to cover it. Okay, and that's our notion of coverage. Okay, so at this point we have two things, coherence and coverage, and how do they play together? Now, hopefully I convinced you with the Asian markets example that you don't necessarily want the most coherent chains, right? It's more like a constraint. A chain is either coherent enough for us or it's not. And coverage is the thing that we're really after. Okay, so the problem becomes, let's find a coherent map that achieves maximum possible coverage. Okay, let me show you what happens when we try to optimize this. You get this map. Again, Greek debt crisis, one line about strikes and riots, one line about Germany, one line about the IMF. What's wrong? I mean, they're important, they're diverse. Come on, you're all thinking that. I mean, it's not really a map, right? It's a set of disconnected lines. And it's especially frustrating when you see this at the bottom that's about Germany and the IMF, and it should have been connected to the red line. So the last property is connectivity. Okay, if two lines are related, I want the map to reflect this. Now, there are plenty of ways to formalize this idea of connectivity, and we try to play with some user studies to see what people care about. And it turns out that people got really annoyed when two lines were related and the map didn't show any connection. But they didn't seem to care much about the type of connection, beginning, end, 1 point, multiple points. So we started very simple, just encouraging pairs of lines to intersect. Okay, so whenever two lines intersect, you score 1 point. Super simple. We later on extended this to something more complex, but this was our first shot. Just if two lines intersect, you score a point. Okay, so at this point we have those three things. We have coherence, that's this optimization problem, LP plus rounding. We have coverage, that's a sum modular function. And we have connectivity, that's a super simple objective about intersection. How do those play together? So coherence, just like before, is still a constraint. And coverage and connectivity, well, ideally I'd like to optimize both. But if I show you a map that's super well connected about something you don't care about, then you probably still don't care about it. Right? So coverage is our primary objective, and connectivity is our secondary. Or the problem really becomes, so consider all coherent maps that achieve maximum possible coverage, and out of those, find the one that's most connected. Okay, and that's on the top here is lexicographical optimization, so the first term is infinitely more important than the second. Okay, good. So let me just give you a one-slide overview of the algorithm. How do you optimize this objective? So your input set is a set of documents. Again, think of them as a result of a query. Now, I said that coherence is a constraint. So ideally, I'd like to enumerate all coherent chains that are candidates to be metro lines. But that's clearly infeasible. So what we do instead, we encode them in the structure that I call the coherence graph. Okay, so each node in this graph is a short coherent chain. And an edge means that you can concatenate them, and they're going to remain coherent. Okay, and it's a transitive property. So paths in this graph really correspond to longer and longer coherent chains. Okay, so this thing really encodes all coherent chains as graph paths. Next thing you want to do is you want to pick k paths from this graph that together maximize coverage of the underlying documents. Okay, so you pick them from the graph, so they have to be coherent, and then you really want to maximize coverage. And luckily, this is just a modular or engineering problem. So we use the algorithms of Chikura and Pal, which is a very nice polytime recursive greedy algorithm with some approximation guarantees. Okay, at this point, we have k chains. They're coherent. They maximize coverage. Now, the last thing we do is just a local search step that tries to increase connectivity without sacrificing coverage. Okay, so let me show you an example of the output. So we started from this very simplistic map about a Greek debt crisis. Now that's the real thing. So you have one line about how Greece struggles to stay afloat and they get help, but is it good enough? And another line about strikes and riots. Another line about Germany, and a tiny line about the IMF. And at this point, you should be looking at it and say, well, OK, it's a cute picture, but is it any good? How do you go even about evaluating this? And evaluating maps is really, really challenging because you don't have ground truth, you don't have golden standard. And I can use all those surrogate metrics from data mining, machine learning, but I'm going to argue that for what we do, user studies are actually fundamental. Okay, we want to, first of all, make sure that we capture those intuitive notions, coherence and coverage, and also that it's actually useful for somebody. Okay, we want to build systems that are useful. So let me tell you about our study. So the first thing we tried to see, the question was, can maps actually help newsreaders understand a news story better than state of the art? And our data set was New York Times, 2008 until 2010, and we picked 3 news stories, the miners trapped in Chile, Haiti earthquake, and my favorite, Greek debt crisis. And the question was, can maps actually help people understand those events better? So here's the first thing we tried, just simple question answering. Okay, so we gave people 10 questions, like how many miners were trapped. And we measure how much they knew before and after using either our system, Google News, or something called topic detection and tracking. Okay, and we had roughly 340 users. And well, we're doing better than competitors, but nothing to write home about. And I asked people, and they said, if I wanted to know the name of the Greek prime minister, I would Google it. I would go to Wikipedia. This is a complete overkill. Okay, and they were right. So I think what we learned is that maps really are not about those small details, about those control F kind of searches. They're really about the big picture. Okay, so we needed to design a second study to see if maps help people understand the big picture. Now, how do you know if somebody understands the big picture? Now, if any of you in this room were ever TAs, you know what I'm talking about. You really understand a topic if you can explain to somebody else. So this is pretty much what we were trying to do. So we asked people to use maps or to use Google News and to summarize the story, 1 paragraph, to somebody who has absolutely no idea. Okay, and then we took those paragraphs, we threw them on Mechanical Turk, double-blind, pairwise evaluation, and asked people, so which paragraph does a better job explain the story? Okay, so we had 15 paragraph writers, roughly 300 evaluations per task, and the results were much better. Okay, in the Greek debt crisis, for example, we had 72% of the people, of the Turkers, preferring paragraphs generated by map users. Now, it didn't look as great for Haiti, and I was curious about why. And I actually went to look at the paragraphs. And it turns out that the Haiti map had 1 major storyline. Okay, there was an earthquake, damages, relief efforts, and then a couple of smaller lines. What was it? Wycliffe Jean running for presidency, and missionaries accused of kidnapping children, that kind of things. And it turns out that everybody that summarized this map pretty much focused on the main line. So I think that the take-home message is that maps are the most useful as high-level summaries for stories that don't have a single dominant storyline. Okay, for the spaghetti type of stories. Okay, good. So this was maps in the news domain. And I started by saying that news is really just an example. Okay, so my goal right now is to convince you that maps are actually super easy to adapt to other domains. Again, that the major principles, coherence, coverage, connectivity, stay just the same. Also, you might be able to use some domain knowledge to come up with a slightly smarter objective. And I'm going to give you 3 examples, science, legal documents, and books. Okay, let's talk about science. So the goal of this one was to see if maps can help students understand the state of the art of some field. Okay, for example, what's reinforcement learning up to? And the data we had was ACM papers, and we did some slight modifications to the objective, mostly because we had beautiful site information in a form of the citation graph. But other than this, the algorithm stayed just the same. Okay, so let me show you an example. So this is a map about reinforcement learning. I don't actually expect you to read it. Let me just show you the major lines. So there's one about the multi-agent cooperative setting, one about MDP-POMDP, another one about controlling robotic arms, one about bandits and exploration-exploitation dilemma, and 1 line about the theoretical bounds and Q-learning. Now, you can see that those are disconnected, but they have all those dashed gray lines between them. That's because in the scientific domain, you might have a line about applications and a line about theory, and they don't really intersect. There's not a single paper that fits in both. But there's clearly been interaction between them, right? Lots of citations. So we also allowed indirect intersections, okay, if there's been citations between them. Let me just zoom in for a second. So for example, this kind of mechanism lets you see that the theory line had impact on the bandit exploration exploitation line, and MDP-POMDP had impact both on the multi-agent setting and the robotic arms. Okay, let me tell you about the user study, because this was a fun one. So the question was, can maps help a first-year grad student understand a topic better than the state of the art? So we basically had a bunch of students coming to my office pretending to be a first-year grad student who's embarking on a reinforcement learning project. And they come to the professor's office, they're all excited, like, yes, teach me everything you know. And a professor gives them a survey paper. Only problem, the survey paper was written in 1996. Okay, so they were really trying to update the survey paper to see what the field has been up to identify the research directions and the relevant papers. And they could use either Google Scholar or maps in Google Scholar. Okay, so just to show you that we had 30 participants. We combined all papers that anybody mentioned into one long list, and we measured both precision, meaning we had an expert telling us this is a good paper, this is a bad paper, and subtopic recall. Okay, so we composed a list of the top 10 sub-areas of reinforcement learning, and we wanted to see how many of those they actually found. Okay, results in a nutshell is that on average, map users managed to find 10% more of their papers were deemed relevant. And out of those top 10 areas, they on average managed to find almost 3 more. Okay, so at this point, we were happy. And just to push this idea a little bit further of maps in science, we actually made a map of our own related work at some point. So this is this work, from connecting the dots to metro maps. I'll show you just what's around. Again, I don't expect you to read this. But there's been lots of work about summarization, and especially news summarization. Some work on narrative generation, and what's a narrative and what's a storyline. Work about coverage notions. There's the pink line about visualizations like concept map and mind maps, and the red line about mapping science. Yeah? Good, so this is maps. Third thing we did was legal documents. So there's a company in Palo Alto that does a legal search engine, and they knocked on our door like, okay, can maps actually help people, help lawyers argue a case? So they gave us Supreme Court decisions. Now, I don't know, how many of you have played with Supreme Court decisions before? They're insanely long, okay? They can be hundreds of pages. So my TF-IDF was completely breaking. So what we decided to do was, when you cite another case, you usually have to say why you're citing it. In blah versus blah, they defined that commerce clause applies here. So if we just use this anchor text to pinpoint us to the most important part of the document, then everything else falls beautifully into place. Okay, just to show an example, we completed one map about commerce clause. So you can see, for example, this purplish line about, first of all, who can waive the state's immunity, and if you work for a state-owned company, can you sue them? Okay, great, what about federal court, and does this section apply or not? So basically asked lawyers for a reality check, if that's actually useful for them. And they said, first of all, that the lines made perfect sense. They were even nice enough to give us labels, okay, so what they think those lines are about. And then again, as a reality check, we computed the words that made the lines coherent from our point of view. Okay, so you can see, for example, the third one, they said 11th Amendment, state sovereignty. We said immunity, sovereignty, amendment, and 11th. Or the last one, that's regulating wholesale energy sale, and we said wholesale electricity resale steam utilities. Okay, so they seem excited about us. Last thing I did, just for the fun of it, I wanted to see if maps can help you understand the structure of a book. And when I say book, I really mean Lord of the Rings. Mostly because I refuse to read A Song of Fire and Ice until he finishes writing it. But that's what we have so far. So there the problem was that my coherence notion, journals are really nice in the sense that they tell you what happened before. Okay, but books don't really work this way. They don't say, okay, now we're done with the battle at Helm and this guy's dead and we can go ahead and do that. They just go ahead and do that. Okay, so my coherence was breaking. So what we decided to do is say, well, one character's point of view is probably a coherent narrative. So focus a lot more on named entities. And just to show you a detail from the Lord of the Rings map, so you can see that the hobbits and Gandalf start walking on their merry way. They meet more people all the way to the council, and then they split. They see Pippin and Merry going somewhere, Sam and Frodo going down there and meeting Gollum. The bad guys are down there, and they're going to eventually meet the good guys. Okay, so there's some structure emerging already. Okay, and let me tell you briefly about what we did recently to make maps even more useful. So the first thing I was worried about was scalability. I really wanted to handle like web scale corpus. So we basically revamped the entire objective. We made everything that I've been saying was embarrassingly parallel into really parallel. And we went down from 11 minutes on 17,000 articles to under 30 seconds per query on hundreds and thousands of articles. Okay, we came up with this hierarchical metro maps, completely different. Second thing I was worried about was interaction. And I actually think interaction is going to make or break metro maps, because I'm not going to nail the right thing based on a couple of keywords. And the nice thing about metro maps is that they have some very expressive interaction mechanisms. So two things we tried was, first of all, multi-resolution. Okay, so you can zoom in to learn more or zoom out to get a high-level overview. And I guess the most interesting technical bit there was we had to do a community detection algorithm that supports dense overlaps. Second thing is word feedback. So remember in the coverage slide, I told you there are weights, they're a good place for personalization. So we actually used some ideas about feature-based feedback. So people can tell us stuff like, well, I don't actually care about Germany, but ooh, Portugal is important, and the map would recompute based on what they told you. Last thing I've been doing this semester, it's been a fun project with a student. So we were trying to find maps for controversial topics, okay, like Obamacare. There's really no one map. It's really based on points of view. Okay, so we defined controversy, and we try to break the document based on their point of view, so really get something like Democrats versus Republicans on Obamacare. Okay, so it's a fun project. One last thing that's been going on this semester, we have a website that's almost ready, like last phases of debugging. And I have a student whose entire mission for this quarter is to come up with an open source package, okay, so people can plug in their data and see what comes out. So it's been an exciting semester. Good, so breathe in, breathe out. The entire point of this project, the metro maps, was you have a news reader or a first-year student or a paralegal or really anybody that has lots of data and needs to rely on search. And we want to be able to show them perspective on their field, okay, so they can see the structure and the connections. So we formalized all those, coherence, coverage, connectivity, and we had user studies to validate our idea. Now, at this point, I was kind of staring at this and saying, well, but what next? What do I not like about this? And the thing I dislike the most about metro maps is you can only see connections, if somebody made them explicit. Okay, if some journalist already told you that those two things are related. What if you want to make new connections? Okay, what if you want to discover something? So this is how the AHA project started, where the challenge was you have lots of data, how do you find the most insightful connections? Or really just like before, you have this fuzzy notion of insight, how do you formalize it? And just a word of caution, so this is work in progress. It's a lot less mature than metro maps, but I've been having a lot of fun with it, so I thought I'd share some. Okay, so again, the goal is to define insight. And there's been a lot of related work. Okay, so there's psychology, cognitive psychology. You can argue that the entire KDD is about taking data and turning it into insight, and also information visualization, right, about data and how do you find the insights. And I was basically reading papers and trying to abstract those ideas, to generalize it. So what have they been doing? So just like before, just stop for a second and think, so what makes an insight? The first thing is really kind of trivial, right? It's about surprise. If you know it already, then nobody cares. But surprise alone is not enough, because give me enough data, I'll find plenty of things that will surprise you, just because they're noise or bias or coincidence. So it really has to be what they call plausible, or really well supported by the data. Okay, it's a super general idea, so let me just demonstrate how this works in the medical domain. And the medical domain is perfect for us, because there's so much data lying around, and every day you see those, researchers found a link between something and something else. So there's potential for so many new links to be discovered. Okay, so the goal was really to build a system that will help people find promising research directions, or really gaps in our current medical knowledge. Okay, so this idea, plausibility, surprise, how does it work? So just for the sake of this presentation, I'm going to focus on a very simple type of insight. So it's basically a pair of medical terms. For example, there's a connection between sleep apnea and diabetes. Okay? So how do you define those things? So this pair is plausible if those two things actually co-occur a lot together in practice. And it's surprising if nobody in the literature ever noticed it. Okay, making sense? So you really see that sleep apnea patients do get diabetes, but nobody in the literature knows about it. Okay, so what kind of data do you need in order to compute those things? So for plausibility, we have 17 years of natural language medical notes from a hospital. Okay, we have 10 million notes. And for surprise, we have 11 million papers from Mellon. Okay, let me just give you an overview of the system we built. So, yeah.
Aren't you missing something important here, which is the importance? If something is surprising and plausible but not important.
Actually, importance, I'm going to get through this in a second, but importance is a part of my surprise notion. We can argue about the words later. Okay? Okay, so this is, I'll show you in a second. I call it utility. So this is our system. Okay, so we start from a query. We don't actually have to start from a query, but researchers seem to have something that they care about usually. So let's start from a query. So for example, sleep apnea. First thing you do is you go to medical notes and find plausible candidates. So what has been happening to sleep apnea patients in practice? Then you take those candidates and you filter them based on surprise, according to Medline. Okay, so in order for this to work, there are three things I should tell you about. Okay, first of all, where the terms come from, what's plausibility, and what's surprise. Okay, so let's talk about terms. So we extracted medical terms from the notes and from Medline. And it was actually a lot more annoying than I expected, because there's this, it's natural language, so there's this issue of granularity. Okay, so people say sleep apnea, acute sleep apnea, recurrent sleep apnea. So are they the same things? Am I allowed to merge them? because otherwise, my counts get completely screwed up. So what we did is we used medical hierarchies. Okay, so you can see, for example, this graph. So migraine disorders has 2 children, common migraine and not so common migraine. That's the kind of hierarchies you get. And we wanted to know if we see something, if you can merge it up. Okay, so what we ended up doing was computing KL divergence. So really, if you use a parent to approximate a child, how much information are you losing? So you can see that common migraine can be propagated up to migraine disorders, maybe even to vascular headache, depends on your threshold. But this other migraine, if you see this, then no, it's a completely different beast. Okay, so those were the terms. Now, given a pair of terms, what makes them surprising? The first thing is pretty much obvious, right? They can't occur together too often in the literature. So we have a threshold. They can't occur more than k times together. Second thing is what Pedro was saying, is that it's really more surprising if those terms are popular. Okay? So if nobody notices a connection between 2 diseases that 5 people in the universe combined have, then I'm a lot more impressed than if sleep apnea and diabetes, they're both really well researched. Okay, so it's really about what I call novelty and utility. Okay? Good, so that's surprise. Now, plausibility actually works exactly the other way around, right? You really want those 2 things to occur together a lot in hospital data. So what we did is we aggregated all the notes that a single patient received in a year. That's our basic document. And the first thing we did was computing Jacquard coefficient. Okay, so how many people have those 2 things versus how many people have at least one. And just let me show you how our system works when you plug in those objectives. Okay, so we start from dementia. And the top Jacquard coefficients are those 6 things. And so the first 3 are really not surprising. It's Alzheimer and 2 medications used to treat dementia. So they're going to be filtered out. But then you're left with hip fractures, wheelchairs, and atrial fibrillation. And at this point, you should be kind of moving uneasily in the chair and say, well, hip fractures and wheelchairs, we might have a problem here. Because it's not really about dementia, right? It might just be because this population tends to be old. So the second part of plausibility is what I call explanatory power. And I'm trying not to use the word causality, but that's kind of where I'm aiming. Okay, so what we do is we find a group of people that are super similar to dementia patients, just they don't have dementia. Okay, and we use propensity score matching to find this group. Then we ask, well, hip fractures, are they a lot more common in dementia patients than in this other group? And if they're not, then we're not capturing the right thing. It's not about dementia. Okay, so let me show you again. So this is plausibility. It needs to have high Jacquard and also pass this matching test. Okay, so this is our system once you plug in those objectives. So you start from dementia. You see wheelchairs and hip fractures don't even pass this matching test. And after you filter for surprise, the only thing that's left is atrial fibrillation. Okay, so this one's like, great, so did we find an insight? Again, how do you evaluate this? Now, ideally, I would make some bold predictions and send an army of physicians to chase them down, but this requires physicians and time and money, which are 3 things I don't quite seem to have. So what we did instead was what we call early discovery. Okay, so the idea is we asked physicians to give us some breakthroughs that happened in the last 5 years. Then we did some time travel, basically truncated in the data 5 years in the past, and asking, so, okay, if you had run this algorithm 5 years ago, how many of those discoveries would you have been able to predict? Okay, and the idea is that if you can predict anything, then it's a really strong indication you have something there. Okay, and like I said, it's super preliminary. They only gave us 4 things, okay? So obesity and colon cancer, type 2 diabetes and sleep apnea, atrial fibrillation and dementia, and incretin and pancreatitis. But the thing is, out of those 4, we managed to discover 2. Okay, so physicians were running around the room, and they're a lot more willing to cooperate right now. Okay, they said they're going to bring us a much longer list. Okay, so I started by saying that this insight in plausibility and surprise is a super yeah?
I'm sorry. So the 2 out of the 4 is a recall measure, but precision, I mean, if you predict 20,000 things.
Oh, sorry. So this was if you start from sleep apnea, is the dementia in the top 3. Okay, so we did a top casing for 3. Okay, and it's kind of hard because I predict lots of stuff, but I can't actually say that anything is false, right? So maybe just haven't discovered. I hope nobody has discovered it yet. Okay, so I said that this was a super general idea, so I'm actually going to show you how the exact same formulation works in a completely different domain. Okay, just same formulation, same algorithm. So that's the domain of commerce. Okay, where the goal is to do a serendipitous product search. So suppose last week I wanted to buy a laundry hamper. Okay, so I don't think you need a hamper. I need a place to store my dirty laundry. Okay, so I actually have a search engine that tries to find products that are plausible in the sense of they solve the same problem, and surprising in the sense that when you go to Amazon, people who view this, then nobody in their right mind who is looking for a hamper was considering this other product. Okay, so the search engine will basically tell you, forget about hamper. Have you considered buying a really big trash can? And by the way, I was talking to a friend of mine, and he said, hey, I use a trash can for a hamper. And I was super happy about this. And just to tell you about the data, so in order to know whether something is plausible, we use ConceptNet. I'm currently working with Chris Ray about trying to find something that's more machine learning, read the web type of inference. And for surprise, we basically scraped 300 million Amazon pages. And my entire point is that the algorithm works exactly the same. The formulation is exactly the same, just instead of medical nodes, to use ConceptNet, and instead of Medline, use Amazon. Okay? And I thought I'd share some topic tips, shopping tips I got from playing with our system, just in case you're in the market. So first thing I learned, that this was surprisingly powerful. Pet products and baby products are surprisingly interchangeable. No, this was really scary. And the other thing is that if you want to buy stuff for your home, then the auto department is a good place to look. Okay, so this was so you don't sleep in the bathroom, so it suggested the car anti-slip mat. And also said, forget about mat, just buy those stickers that people put on their staircase. So I don't know, I've been having fun with the system. Okay, AHA project. The whole point was to help medical researchers discover some promising new ideas. Okay, and we did manage to do some early discovery of medical breakthroughs. Now, there are plenty of applications in other domains. I only talked about serendipitous product search, but we also did a literature-based discovery and something about adding stuff to Wikipedia. Now, this seems like a good time to take a step back. Okay, so what did we have here? We had Metro Maps and the AHA project. So what's the underlying theme? What's the thread between them? So it's really, well, first of all, there's the big picture of, you have heaps of data, how do you turn them into insight? But the flavor of problems that I really care about are the ones that start with a super fuzzy problem definition. Okay, so what's a coherent storyline? Or what is insight? And then again, how do you formalize those things mathematically, and how do you optimize them? And ultimately, you need to tie it to a user study, okay, based to see that you capture the right thing, and also that you make something useful. Okay, but this idea of starting super fuzzy all the way, closing the loop with user studies. Okay, in order for this to work, I basically use tools from data mining and machine learning and information retrieval, lots of HCI, visualization, algorithms, especially graph algorithms. So that's what comes in. What comes out, I'm trying to apply those ideas in as many domains as I can find. Again, these are some of the ones we talked about today. So medicine, science, news, legal documents, commerce, and literature. Okay? So this is what I currently do. Let's talk about what I want to do next. So first of all, the Insight project. Okay, it's at the very beginning, and I really want to build a set of tools that will let anybody, okay, so scientists, analysts, web users, you name it, just plug in their data and find the most interesting bits and pieces. Okay, and ultimately be able to enable new discoveries. And I really want to stress that I really care about using the same technique across multiple domains. Okay, so generalization is, for me, a really good indication of the power of a technique. Now, I told you about some of the domains that I already play with. Let me tell you about some of the collaborations I'm most excited about. Okay, so first of all, I gave a talk at the Stanford Social Science Conference, or Computational Social Science Conference. And there were a bunch of social scientists and political scientists showing up at the end of the talk like, hey, we have data for you, which is awesome. Okay, they had Congress nodes and crime data and lots of really, really fun data sets. Life sciences. So we did it for medicine, but I really want to find somebody who knows something about biology and where this could apply. History, let's say there's a history professor that really wanted to apply metro maps to telegrams. Personal data, okay, personal data is something I've been dying to do for a really long time, browsing history. Okay, so suppose you're trying to plan a trip somewhere and you all of a sudden find yourself with 75 open tabs in Firefox, and wait, what just happened? So really to be able to kind of see, okay, here's the last hour if you're browsing organized into a map. What else? There's been interest from corporations about how to organize their data, some financial data. I've been toying around with this idea of insight for investigative journalism. And the last thing here, well, the last thing actually surprised me. Okay, I never thought this would work for anything that's not text-based. But there are a couple of researchers at UT Austin that applied the methods to summarize videos using sequences of images. So I don't know, apparently it works for images as well. I seriously wasn't expecting this. Okay, so that's one thing. Now on the longer term, now there are so many fuzzy terms that just wait to be formalized. Because I told you this semester I've been working on controversy, for example. How do you formalize it? But out of those, I guess the real holy grail, the one I care most about, is creativity. Okay, and let me tell you just briefly about something I started this semester. How do you tackle this problem of creativity? So here's the scenario. You own a company, you own some product, you have the technology, and you want to expand your business by changing this product somehow. Okay, so how do you change your business? And we follow something called a Scamper model. Okay, it's basically a set of questions like, what can you substitute in your product? What can you combine it with? Can you reverse the functionality? That kind of questions. So my favorite example is this company that used to make shower heads, like water pressure shower heads, and now they're making water pressure dental floss. I thought this was brilliant. So we basically built a prototype system using the same ideas, okay, of the laundry hamper example. So how do you answer those Scamper questions using ConceptNet? How do you filter out the obvious things using Amazon data? Okay, so this is what we have. So we have a search engine. I'm just going to tell you about like one example output. So you type in alarm clock, and it basically spits out suggestions like, how about combining it with a coffee machine? So you wake up to a fresh cup of coffee. Or how about combining it with a dimmer? So the room becomes more and more light as you're supposed to wake up. Or maybe make a silent alarm clock, maybe something that vibrates, either for deaf people or if you don't want to wake somebody up. He just keeps spitting up suggestions. So, do you know Sky Mall? The thing you get at the airplanes. So I think I'm kind of at the stage of where I'm giving them ideas, but hopefully it will become better later. Okay, so that's the creativity thing. Okay, again, breathe in, breathe out. The whole point of this talk was that we have plenty of data, and it's great news, because data can help us understand the universe and make better decisions. But in order for this to work, it's not enough to collect this data or search through the data. We actually have to make sense of it. So we did this thing about how to reveal structure in the data, metro maps, again, coherence, coverage, connectivity, and how to discover unknown connections, the InSight project. And we had some user studies and early discovery in order to validate our ideas. Now, if there's one thing I want you to take from this talk, it's probably this image right here. Okay, so you really have to go beyond just search. That's about it. Thanks.
Time for a few questions.
Oh, come on, you know all.
So for your AHA project, I think one of the more interesting things is not just saying there's a connection between A and B, but why there's a connection between A and B.
So to say why there's a connection between A and B, not just that there is a connection. So for the medical data, I'm currently working on adding justification. Okay, so I say, well, there's a connection between sleep apnea and diabetes, and here's a set of words that tell you why this population is different, especially from this propensity score matching population, which is a very good reality check, because every now and then you can actually look at it and say, oh, okay, I'm capturing something completely wrong. Making sense? Yeah, but you're totally preaching to the choir here. Yeah, hi.
So one possible objection to this style of work is that there's a fairly low ceiling to the kind of discovery or understanding that you can achieve, right? Because you need to do these things, so like, for example, discover new products. You need a deeper understanding of what goes on, like radar. Mm-hmm. How did radar give rise to microwave ovens, right? Well, it turns out that it heats things, and people need to eat things to cook them, right? But where are you going to get that kind of knowledge to do this kind of discovery?
There's no way on earth I'm going to repeat the whole question, but basically that there are things that I can't capture with my notion of creativity. So yeah, one of my favorite examples.
I don't just mean creativity in particular, but this whole line of work. Like, for example, do you, to build a good metro map, need to understand something about who are the agents involved and what's driving them, etc.?
So two things about it. First of all, is whenever I
Repeat the question.
Oh, come on. Really, you couldn't hear him? So the idea, okay, how about I just reply to it? Would you forgive me? Thanks. So about, okay, so whenever I submit a paper about metro maps, there's always one reviewer that says, this is great, but too shallow, how about you slap semantics on top of it? And I'm completely for it, as long as I find somebody who knows semantics who's willing to tell me how to do this. Okay, so part of this goal of this project was to see how far you can push really, really stupid features. Okay, so named entities, noun phrases, and whether you can actually get good results from them. And I completely agree that that's a limitation, that you can actually, give me smarter features, I'll probably get something smarter. Or in the creativity domain, one of my favorite examples is, not even creativity, sorry, before this, the laundry hamper. So there's an entire repurposing community of people who are basically insane and they find new uses for things. So they take, what do you call it, floaties, like kids' floating devices, and they use them to protect wine bottles in a suitcase, which is something I'll never be able to do without the physics, right? So I was actually looking into stuff like, there's a website of how stuff works, and I was trying to find if I can actually get some info from there, or what I said about Chris Ray. So I've been trying to extract more properties, more physical properties. But yeah, I mean, I'm totally with you. The more properties, the better. Answer?
So in your importance term, in the second product, I guess, you're taking the minimum of the frequency of the two terms?
Yes.
Why not the maximum?
Because if you find a link, okay, sorry. Why do I take the minimum and not the maximum, the importance, the utility of the plausible, surprise. And if I find a link between diabetes and, again, this disease that one person in the world has, then it's probably not going to have a big impact, right? I really want both of them to be really, really important. But by the way, on a more general note, and as much as I love sitting in a dark office and crafting objective functions, I'm not married to either of them, okay? So one thing I've been thinking of doing recently is define kind of an expressive grammar of what the functions can do and then just learn them from feedback. Okay, so have people actually interacting with the maps and telling me, well, this isn't coherent, and or this line is not coherent enough, or I don't care about this line. So I can kind of learn an objective instead of coming up with those functions myself. Wait, but did I convince you about the minimum? Okay, good.